You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. David Curtin for a discussion of dark matter. Dr. David Curtin is a high-energy phenomenologist interested in finding and analyzing theories of particle physics beyond the standard model. His area of research focuses on cosmological and astrophysical signatures of complex dark matter, particularly focused on atomic dark matter, which has deep theoretical roots in theories of neutral naturalness and gives rise to rich dynamics that produce mirror stars and dark galactic disks.
Dr. David Curtin, welcome to the program.
Thank you so much, John. Thank you for having me.
Now, this particular episode is going to get interesting because we are dealing with the most mysterious something that we know of in physics right now, other than maybe dark energy, but dark, which may be related for all we know, but dark matter. And we see ample evidence of this from several different avenues. We see indications of the presence of dark matter, sometimes very big, such as galaxies not flying apart. Well, what we haven't successfully done is figured out what it actually is, other than it produces gravity. That's all we know. So the best explanation we have so far is a WIMP, a weakly interacting massive particle. But what does that actually entail? What is a WIMP?
Yeah, absolutely. So I'm going to give you my sort of high-level view of the dark matter situation, and I'm actually going to start not with a type of particle, but what we know to be true about it empirically. And what we know to be true about dark matter is that it makes up the majority of the universe's matter budget, something like 80%. Yeah. And we do know from the way that it affects the cosmic microwave background and the way that it affects the shape of galaxies. And also you can, using gravitational lensing, you can get somewhat direct, kind of like an image almost, of the matter distribution of dark matter in galaxies. And an empirical thing that we know to be true is that the dark matter halos, which are the majority of the mass in galaxies, which kind of surround the visible bit, they're much bigger. They're much bigger than the visible bit, and they're mostly spherical and puffy. And what that tells you physically is that most of the dark matter, and I'm choosing my words very carefully here, most of the dark matter appears to be collisionless on astrophysical scales. So what that means is, as the universe evolved from its early days after the hot Big Bang, gravity is pulling together matter, and that'll eventually become galaxies. The normal matter that we're made out of is made of atoms. Back in the early days, mostly hydrogen and helium. And the point is that stuff collides with each other. It kind of essentially, as it collapses, it turns into a plasma. And that plasma can cool because we have electromagnetism, and that allows normal matter to emit photons. And if normal matter cools, that means it's losing energy. And in galaxies, that means it collapses into the center. And that's why we have these relatively small visible parts of galaxies, like the Milky Way, in the middle of a big sort of galactic halo, whereas the dark matter that is kind of 80% of the mass remains, for the most part, fairly spherical and puffy. And that tells us just very empirically that this part of dark matter is unable to shed its energy. And that tells you it's essentially collisionless for the most part. That doesn't mean it doesn't collide at all or doesn't interact at all. It just means that whatever that interaction rate is, it has to be below some amount. So that's the sort of empirical description, at the risk of being long-winded. But I think it's an important thing to have in your head, because that's what, I'm a particle theorist. As a particle theorist, that's what we start of when we try and think of what it might be. So you said the best explanation we have is the WIMP. There's a lot to unpack there. Let me unpack two things. The first one is the WIMP is a popular dark matter candidate because it is a very general type of particle that does not interact much with itself astrophysically, and therefore, if dark matter is that, then that would be consistent with what we see, basically. People say it's the best explanation That's a sociological artifact. And the reason the WIMP is so popular is because of its association with a very important class of theories called supersymmetry. And supersymmetry is something that was, by now it's in the 80s or so, many decades ago, it was first proposed as a solution to a truly fundamental problem in particle physics, which is called the hierarchy problem. And very basically speaking, that is the weird observation that you have four fundamental forces that we're aware of, the weak and strong nuclear forces, the electromagnetic force, and gravity. And once you account for the fact that some of those forces are short range and so on, gravity is the weakest by just dozens of orders of magnitude. So that's confusing. Why is gravity so weak compared to these other forces? And another way to phrase that question is gravity talks to things proportional to their mass. If you're heavier, then you feel gravity more. So the other way to phrase this mystery is, why is normal matter that we're made of so light compared to whatever scale would make gravity strong, which is the Planck scale? This is called the hierarchy problem. And without going into any details, supersymmetry solves the hierarchy problem. And part of the package of supersymmetry, its minimal versions contain a WIMP. So this was kind of this default theory in the 90s and 2000s for what is our most neat, most best, most theoretically clean hypothesis for what the next sort of level of the standard model of particle physics would be, the next layer of the onion, the extra pieces. Because if you have supersymmetry, you solve the hierarchy problem, and a WIMP comes along for a ride, and you solve dark matter at the same time, and that is fantastic. So that's very attractive, and that's responsible for it becoming, that's largely responsible for it becoming kind of a default. But that's what the WIMP is. So the WIMP in general is a class of particle. Maybe it's as heavy as a proton, maybe it's 1,000 times heavier, but something in that range. And it interacts very little with itself on astrophysical scales, and it has no long-range interactions. So it's not like an electron or a proton. And that roughly fits what we see in the universe today for the majority of dark matter. But, and maybe I'm preempting a little bit, the two problems with that story are, number one, we have not seen supersymmetry or anything like it so far, despite decades of looking. And number two, this empirical picture, even if something like WIMPs are the majority of dark matter, and something collisionless kind of has to be, there are strong theoretical reasons to consider the fact that dark matter is more than just one thing. So then you are opening a bit of a Pandora's box. So yeah, let me pause there.
Yes, but that's how normal matter works. You know, I mean, it has...
Exactly. No, that's right. No, you're so right, right? Like, there is this, like, common sense argument, like, the world is pretty complicated. Even, there's electrons and protons and neutrons and quarks and photons and gluons and W and Z bosons, and they make all this complexity. And that's only, 6% of the universe, or 20% or something like that of the matter budget. Why would the other 80% of matter be this one boring thing? Like, so that's a very, like, common sense plausibility argument for why dark matter could be more complicated. Absolutely.
But that is where the sea monsters and big feet and such lie in this, because it could be extremely complex. We'll get to that in a bit. But first, all right, so WIMPs seem to fit from a certain point of view. But there's one other thing, is they sort of look like a neutrino in a way, in that it's a weakly interacting particle. The problem is we've never seen it interact. And neutrinos, we have been able to, although it was very hard, but now we have. We've seen them. So is there any hope for experimentally detecting dark matter through some kind of occasional interaction like a neutrino?
So that hope, I think, is definitely there. I mean, so, we can talk a long time about, I think what you're referring to is essentially kind of like detectors deep in some mine or something, very clean detectors that look for tiny collisions of dark matter with the detector material. And, that's really, these experiments are very challenging. They've come a long way. I think, without going into too much detail and a lot of the things that we can discuss there, absolutely, there is still a lot of hope to find a signal there across a wide variety of masses. You could have a wide variety of possible interactions. Maybe it only interacts with electrons. So then you'd have to have different detector technologies. Maybe it only, maybe it interacts differently with neutrons and protons. Maybe the interaction. So there's this like elephant in the room about dark matter detectors, which is that, like, exactly like you say, it's kind of like neutrinos. And in fact, we know that we're bathed in a background of neutrinos. The sun makes them. There's just kind of galactic neutrinos flying around that are made in astrophysical events and so on. So there's this background level, this background noise of neutrinos. And there is a component of that would show up in dark matter detectors if they are sensitive enough. Now, so far, we have not made detectors that are that sensitive, but we're getting there over the next decade or so. That's called reaching the neutrino floor. So it's almost like building a microphone. And if you make the microphone too sensitive, you can start hearing the bugs crawling in the room. You know what I mean? And then making it more sensitive will not allow you to hear things better because all you hear is the bugs crawling in the walls or something. Yeah. So the neutrino floor is this thing that kind of lies in the future of dark matter detectors. And once the detectors become sensitive enough to detect that, then you suddenly start having a background to dark matter detector events. And then it becomes much more difficult to become more sensitive than that. So long story short, it's entirely possible for even kind of cookie cutter WIMPs to have an interaction with normal matter, but for that interaction to be just weak enough that it's drowned out by background neutrinos in our experiments. So we absolutely still could find it, but it also could interact a little bit, but just be very, very difficult to see. So that's kind of a very interesting story by itself, but that's where we're headed.
So given that sort of similarity with the neutrino, one of the great things is we are able to increasingly study neutrinos is the cosmic microwave background radiation equivalent in neutrinos, meaning the neutrino background. And this could give us great insights into the early stages of the Big Bang. Do you envision that once we figure out what dark matter is, we could use that as a probe in the early universe in a similar way?
That's a really interesting question. Maybe. The cosmic neutrino... So I don't know how technical you want to get here, but the cosmic neutrino background was... Yeah, it's like the cosmic microwave background that we see with photons, but it was created when the universe was something like 5 orders of magnitude hotter than it was when the cosmic microwave background was created. The cosmic microwave background was created when the universe had a temperature of the equivalent of roughly 1 electron volt, or about 10,000 Kelvin or so. And the neutrino background froze in at a temperature that's roughly 100,000 times greater than that. So indeed, it contains information about an earlier era of the universe. The detection is one of the holy grails of these kinds of experiments, and it could absolutely reveal interesting information, but it's very difficult, and it might be a little while until we get there. Yeah.
Far future physics.
Indeed.
Now, models of dark matter other than a WIMP, in other words, there have been some other ones advanced. What are your views on those? For example, a really, really wacky one that I know of is the idea that non-locality and we could just be seeing an echo of the normal matter amplified somehow. So there's all these ideas other than WIMPs. Do you think any of those have legs?
So let me separate the alternative to WIMPs into things that I think are sort of entirely standard versus those that I think that are on a different level of wackiness, as you say. So within particle physics, and as a theoretical particle physicist, it's my job, to come up with various hypotheses for what essentially could the possible particle content and force content and other characteristics of the universe be. And a WIMP is a type of particle that you're hypothesizing with a certain mass, certain interactions. I can hypothesize other types of particle. I can hypothesize that there exists an axion. It's a certain type of particle that actually could help resolve some mysteries in nuclear physics. I could hypothesize various other types of particles or things that are more or less WIMP-like. I can kind of do that till the cows come home, and that's theoretically, if you want to distinguish between those, it's kind of a matter of taste. It's also a matter of, okay, can and should you root this in higher theoretical considerations, like trying to solve other theoretical problems at the same time, just like supersymmetry solved the hierarchy problem, the weakness of gravity, while kind of spitting out a WIMP. So that's neat. Is there other examples of this? So imagining other particle types, they're just hypotheses that you write on paper. That's no more or less wacky than a WIMP, and there's a few of those, and in my mind, those are all perfectly viable candidates. And we do have to be very, very open-minded about this stuff because we haven't seen anything, just like you said. graduating slightly to a somewhat higher level of wackiness, things like this non-locality business and so on, to be completely honest with you, some of this stuff becomes highly, very, very speculative and maybe a bit harder to root in sort of certain theoretical considerations and sort of hard to flesh out in great theoretical detail. I'm also not a super expert on those things, to be completely honest, but there's kind of a reason why they're wacky. Like if they made immediate sense, everyone would be working on them. So I kind of want to leave it there if that's okay, because I'm not sure I can comment in much more detail on the sort of highly wacky things. But for sure, all kinds of different particle types are all fair game. Axions, WIMPs, right-handed neutrinos, atomic dark matter, whatever particle types, those are all theoretically really not that weird. Yeah.
And it has to be said that what's really not weird here is that the behavior of normal matter. We know how it works. We have hydrogen, helium, all the way up to uranium and beyond. We have all of these enormous complexities within normal matter. Now, one of those particles, probably the most important one, is the proton. So could there be, if we're going to talk about a particle, could there be a counterpart of dark matter that is analogous to a proton?
Right. So I think the answer is absolutely. So let me basically riff on what you're saying. Like in particle physics and in quantum field theory in general, the mathematical language within which we like to think is rooted in symmetries. Now, without going into detail, fundamental forces like the strong nuclear force or electromagnetism are actually described as sort of forms of symmetries in your theory. And supersymmetry, it's right in the name, right? It introduces a hypothesized new symmetry, and symmetries at the level of fundamental laws require certain things to be true, otherwise they're not symmetries, right? Like if you have, a soccer ball in America, yeah, and the fact that it's round imposes the requirement that, it has a certain shape, right? So having a symmetry be part of your fundamental laws requires certain things to be true, and in the case of supersymmetry, it requires the presence of certain extra particles, one of which kind of is the WIMP, yeah? So that's why it's neat, yeah? So that's how particle theorists think about the world. The standard, like our matter, the stuff that we're made of, we have all these forces, we have all these particles. Proton is made of quarks, so a bunch of quarks make a proton. We also have electrons. A bunch of quarks can also make a neutron. Proton plus electron makes hydrogen. Protons plus neutrons make the other elements, and so on. Yeah, so complexity builds because you have a few forces and a few particles. They can interact in this interesting way. Now, there's two ways to think about having something like a dark proton. One of them is, just like you said, based on just common sense plausibility, right? We have so many different kinds of particles. We have different quarks making electrons, making protons and neutrons. We have electrons that can form all these interesting systems and bound states. What if there was a dark proton and a dark electron that interacted via some version of dark electromagnetism? It is in some sense a much, much simpler, but minimally, it's a much, much simpler version of what we have for normal matter, but it's kind of minimally more complex than a simple WIMP. And then the empirical question is, could this be all or part of dark matter? And that's an important question. It could be part of dark matter, yeah? And you could even go further. Like I was hinting earlier at, the reason why the WIMP is so popular back in the day anyway, is that it could also be justified with supersymmetry, which solved other problems. There are other theories, supersymmetry as a solution to the hierarchy problem, to this question of why is gravity so weak, has come under, diplomatically we call it experimental strain. Yeah, like we haven't seen its predictions at the Large Hadron Collider. And there are other families of theories that solve the hierarchy problem, that explain the weakness of gravity or the lightness of the Higgs in a certain way. Let me not go into detail. And they actually predict no signals at the Large Hadron Collider, but the symmetry essentially dictates that part of dark matter or part of some dark sector is essentially a kind of copy of the standard model. The symmetry copies the standard model particles, electrons, protons, neutrons, photons, gluons, all these things. they're copied to the standard model into their own little version. So you'd have dark electrons interacting via dark photons. You'd have dark quarks interacting with a dark, strong nuclear force, forming dark protons and dark neutrons. They would form dark atoms with the dark electrons. So this particular example is called the mirror twin Higgs. So it's a theory that was invented by Zaccaria Chaco and friends in 2006, and it has since become a sort of baseline poster child for this alternative way of solving the hierarchy problem. And just like Susie predicted the WIMP, and isn't that neat, the mirror twin Higgs predicts dark matter to be some fraction of these weird dark atoms that have all the qualitative features of our matter. So they have dark protons, dark neutrons, dark electrons, they form dark nuclei, dark atoms, all that business. But the details, the exact masses of the protons or the exact strengths of the forces, all these things are not so well set. So they could vary by quite a bit, and that is very interesting. But the qualitative ingredients, the particle types and force types, are actually the same, or at least related to the ones that we see. So that is a strong theoretical reason to carefully investigate this possibility of dark complexity. Yeah.
Now, dark complexity, how far does that go? So you have dark atoms and counterparts of the periodic table, essentially a mirror of it. Does that go up to dark chemistry, molecules?
I mean, the short answer is absolutely, it does. I want to say that in some sense, hypothesizing this, the interesting thing is that something like the mirror twin Higgs, which predicts these dark atoms, dark nuclei, and so on, in other words, it predicts this particular type of atomic dark matter, as a theory that I write down on paper, it's really quite simple, and then it just spits out this prediction, right? But like I said, you essentially have dark nuclear physics, dark chemistry, dark atoms, and so on, but many of the numbers, the details, could be a little bit different. For example, the dark electron could be a few times heavier than our electron, which affects things like atomic binding energies. Yeah, the dark proton and dark neutron could be a little bit different in mass, or quite a bit different depending on the exact details of the theory. So this is not determined, uniquely. And the point is, imagine all the work, the centuries of work that we, as a scientific community, as a species, have put into understanding nuclear physics, chemistry, and so on. And we know how this works because we see it. We can also just go measure it, right? I knew the binding energy of carbon, and I knew the chemistry of carbon before I could predict it from first physical principles and theoretically calculate it with nothing but the fundamental laws. But if we are hypothesizing something about atomic dark matter and whatever its complex behavior is, we're starting with the fundamental laws, and we're trying to calculate outwards what it does. And I when I give talks about this in an academic setting, I kind of joke that this is kind of like alternative universe physics fan fiction. Like what would chemistry be like if the electron was 5 times heavier than it is? And for sure there would still be chemistry, but the details of it would be different in ways that I have no idea how that shakes out, right? I don't know what dark molecules are stable or what their sort of, various properties are. Like that's a very detailed question. But qualitatively, if the mirror twin Higgs gives you atomic dark matter, is there dark chemistry? The answer is yes, absolutely.
So the next logical step to ask about would be, could that chemistry be similar enough to create, well, obviously it probably very well would, dark planets? In other words, counterparts to planets in the dark matter sector.
Basically, yes. So like I said, so let me zoom out for 1 second. And so the short answer is yes, but let me zoom out for 1 second and give a bit of context to my answer and to your question. When you think about what our types of atoms, the stuff that we're made of, when you think about what that does in the universe, most of the important effects are captured by just the physics of hydrogen and helium. The universe, shortly after the Big Bang, made the heavy elements. For the most part, it was kind of like 3/4 hydrogen, 1/4 helium by mass, kind of a bit of other stuff. And then with only those 2 elements, you have gas. That gas can cool. It can form Milky Ways and galaxies. That gas can cool further and form stars. And those stars can radiate and shine as they gravitationally contract. And sure, if there's nuclear physics, then they shine longer because they can have nuclear fusion, but they can actually shine for quite a while even without nuclear physics. So a lot of the galactic and sort of astrophysics is really coming down to the chemistry of hydrogen and helium, the elements that you start with shortly after the Big Bang. And that sort of suggests to you that when you try and seriously study this possibility of more complex dark matter, we study a sort of simple, in many of our investigations, we study a simplified version of atomic dark matter that's just the dark proton and just the dark electron. And that still gives you super interesting astrophysics. It gives you dark galactic disks. It gives you these dark stars, yada, yada, yada. And that's kind of how we slowly make progress on understanding, bit by bit, what this stuff could be doing in our galaxy so that we can try and predict its behavior and try and find it. But, if you then say, okay, well, let me not be beholden to this minimal simplistic scenario of atomic dark matter. Let me adopt this theoretical motivation of solving the hierarchy problem. Let me pretend I'm in this particular theory, for example, the mirror twin Higgs or something like it. Then I don't only have a dark proton, I have dark nuclear physics, I have dark neutrons, a dark periodic table, dark nuclear fusion. And then, unequivocally, you form stars. Those stars have some kind of nuclear processes happening on the inside that prolong their life, where they shine in dark photons. So again, just to be clear, these dark stars would be invisible to us, but they would shine in dark photons and illuminate the dark world, right? And these nuclear processes would create heavier dark elements. And so there's a crucial question here. If the physics of dark stars is such that these heavy elements are expelled, right? So because we have to think about our world, like why are there normal planets? The reason there are normal planets, if the universe only started with hydrogen and helium, is that heavy stars make heavier elements all the way up to iron, and then they explode in supernova and spew those elements into the interstellar medium. And that's what you can then make planets out of in the next generation of stars. Or neutron stars can merge, and these neutron stars create elements heavier than iron and spew that out, when they merge. So the creation of heavy elements relies on these stellar forges, but then also being expelled from these stellar forges. And whether or not those mechanisms of expulsion or liberation of the heavy elements would be active in one of these dark sectors is an open question. But in some sense, why wouldn't they be? So it's certainly plausible that they're active. And if the physics of dark stars is such that the produced heavy elements are expelled, then yes, these heavy elements, heavy carbon, heavy magnesium, heavy silicon, oxygen, iron, the stuff that planets are made of, or whatever the dark equivalent is that makes solid matter and dust and whatnot, would form dark planets. And all the other fun implications of that, absolutely.
The other fun implication being dark life, which, that, of course, we would need to know a lot more than what we do, but it's there.
You would think so, right? It almost introduces like a Fermi paradox squared, right? Like we don't really know how likely life is in our universe. I liked your episodes on the Fermi paradox, by the way, but I myself can't think of a particular reason why life for our matter would be super rare. So I take the Fermi paradox very seriously, and I'm happy to have a long conversation about it, but maybe that's for another day. But again, we don't empirically know how likely life is with our matter, right? So in some sense, the question is even more mysterious for this unknown dark complex matter. But again, just operating on sort of qualitative plausibility arguments, if you have dark chemistry and you can have dark planets and these stars live for a long time and so on, it's kind of hard for me to imagine that it's impossible. Let me put it that way. But that's a lot of ifs, right? This stuff has to exist first, and we're looking for it, and that's a big question. But just to get to the fun implications, that's an absolute possibility that I take seriously.
Now, there is something glaring here that I think is, as we establish and learn more about dark matter, should that be possible, and we do, why is there so much more of it than normal matter? We're talking about symmetries. That's one heck of an asymmetry right there. So is there anything in that could be at play here in understanding the nature of dark matter?
You're completely right. That is a big question. And it's one that we take very seriously and we investigate theoretically. Let me give you one possible answer, okay? the stuff that we are made out of is about 15-20% of all the matter in the universe. If there are some symmetries so let me wind back a little bit. Why do we exist? That's like, why is there any matter in the universe at all? And at least for normal matter that we're made out of, this requires something very non-trivial to happen in the early universe. It requires something called baryogenesis. So this comes from baryons. Baryons is protons and neutrons. That's what we're made out of. And genesis is creation. So the early universe started with an equal amount of matter and antimatter. And roughly the reason why I know this is because essentially that's what comes out of inflation. So we can have a long conversation about why does inflation make sense. But taking that as a given for the moment, the universe started out with an equal amount of matter and antimatter. And what we know empirically is that at some point during the Big Bang, some dynamical physics happened, some process, some set of interactions, some phase change, something. Whatever it was, it created a tiny imbalance in the sort of plasma of normal matter. And that tiny imbalance switched 1 in a billion pieces of antimatter to a matter, such that after this process was completed, and we don't know when it happened exactly, you had 1 billion pieces of antimatter for every 1 billion and 1 pieces of matter, the stuff that we're made of, quarks and electrons and so on. And once the universe cooled, as the hot Big Bang proceeded, this matter and antimatter annihilated away. We know that matter and antimatter makes a Big Bang and goes away into light and energy and so on. But the 1 billion pieces of antimatter, the 1 billion and 1 pieces of matter only had 1 billion piece of antimatter to annihilate with, and you have 1 piece that's left. And that 1 in a billion is everything that we're made of and that we see, galaxies, planets, life, you and me. That's that 1 in a billion leftover. So that's baryogenesis. And the way that this proceeds is another one of those big mysteries in physics. Yeah, we have lots of ideas, but we don't know which one's right. So now attacking this question of why is there more dark matter or than normal matter, and what about atomic dark matter and so on, fair enough. In general, the fact that dark matter and normal dark matter have a similar amount of each, but somewhat more dark matter, only a factor of 5, is mysterious. But if you have something like atomic dark matter and you have this symmetry that relates it to the standard model, you'd certainly expect certain symmetries to be existing that sort of whatever baryogenesis happens to make normal matter that we're made of, some version of that process has to happen for the atomic dark matter as well. But we've written papers about this. That process is so sensitive. We know that the dark sector is very unlikely to be an exact copy of the standard model. For various reasons, there will be differences. And those differences can easily be enough to change the amount of atomic dark matter in the universe from being the same amount as normal matter to a tenth to more. So the actual amount of atomic dark matter that you get can be really variable, depending on details of the theory that we don't know. But it's certainly very plausible that just like the standard model is 20% of dark matter, is 20% of all the matter in the universe, whatever this atomic dark world is, this atomic dark matter or whatever, it could be 1%, 10%, 20% of all the matter as well, right? And then the rest, the remaining 80, 70, 60%, whatever it is that's not atomic dark matter, could still be a WIMP or something else. It could be an axion, right? So that's an open question. But this symmetry to the standard model matter suggests that whatever created normal matter, some version of this created the excess amount of atomic dark matter, and then within understanding that process, you could have a wide variety of abundances, but something like the amount of standard model or a bit less, a bit more is completely plausible. But we don't know exactly how much.
I think that gets into, again, future physics, because you could ask the question, maybe in the future when they learn more, they'll be asking, well, why wasn't there more anti-dark matter at the beginning of the universe to annihilate that amount of mass? Or, as you said, differences between the two anyway, inherently. But that's just it just goes to show you how little we know about physics right now.
I mean, absolutely.
By its nature, as of right now, we don't know almost nothing about 80% of the universe.
So, I mean, you're right. You're completely right. But I think, again, it's a qualified what we don't know. In some ways, it's a boundless, exciting territory. But in other ways, we have a variety of mathematical tools, essentially quantum field theory, to describe the various types of dark matter. And that allows for a huge amount of variety. It allows for these dark protons, dark electrons. It allows for WIMPs. It allows for axions, whatever. But there are still mathematical rules that you have to follow when you play this game, when you devise these hypotheses. And that's why we can make serious predictions. That's why we can try and search for these things in a serious way, right? Like, it's not a completely free-for-all, but great art comes from constraints. There are constraints, but the possibilities are still incredibly huge and wide and exciting. So that, to me, makes this so thrilling. It's an incredibly thrilling time in science. Like, we kind of know some of the rules, but there are these glaring missing puzzle pieces, and we have to play within some of those rules to find the answer, but the answer could be so many things, and it's just deeply exciting.
And now to dark stars, to deep
Yes.
dive into that and your recent paper on this. The idea of dark matter actually interacting gravitationally comes together in a certain way where it may be detectable through an interaction with normal matter in the form of a dark star that could be distinguished from a regular star. Tell us about that.
Absolutely. So the sort of key... So again, one of the impressions I want to leave you with is that the implications of our research are potentially awesome and in some ways wacky, and it sounds speculative, and it sort of is in the sense that we don't know if it's true or not, right? But we're coming at this from these incredibly theoretically sober, grounded investigations, right? So in that, I already told you how this notion of atomic dark matter can be theoretically motivated by looking at this other deep mystery of why is gravity so weak, and then this thing gets spat out as a prediction, right? Just like supersymmetry spits out the WIMP, yeah? So let's keep going, right? Look, if this dark matter, if part of dark matter is this atomic dark matter of whatever type, then indeed, because atoms of any type, being a heavy and a light particle like a dark electron, dark proton, interacting with some version of electromagnetism, some exchange of something like a photon or a dark photon, that stuff will be able to cool, it'll be able to have long-range interactions. It can bump into itself, it can jiggle, it can cool, it can collapse, form galaxies, form stars. That's how that works, okay? Fine, so you have dark stars. And indeed, if the only thing that you could do is look for the gravitational signatures of those dark stars, you could still look for what's called gravitational microlensing. So these little dark stars are like tight, dense, just like normal stars. There are these dense amounts of dark gas they're these little balls, and even if they're invisible, if they fly in front of a star from our point of view, they could act as a gravitational lens and momentarily brighten the light of that star. So even without these various interactions, you could look for these things, and there's ways that you could imagine discovering them that way, and that's really exciting. But that's not what we're talking about right now. We're talking about, okay, fine, what if it interacts with us in some other ways? So now, let me tell you about dark photons and normal photons. So we know about normal photons. That's how we see. That's how electrons and protons make atoms, and so on. That's the mediator of the electromagnetic force. If dark atoms exist, then there's a dark photon. And for the potential technical people in the audience, let me say it's a massless dark photon. Just like our photon has no mass, let this dark photon have no mass. Now, the thing about photons or dark photons that's really interesting, and it's kind of unique among the various types of force carriers, is that a photon by itself has no charge of any kind. It's neutral, right? Like, and we kind of know this, like you can't deflect a laser beam with a magnet, right? So a photon does not carry any electric charge, and a dark photon would not carry any dark electric charge. Now, for these symmetry reasons, that means that there's actually no quantum mechanical reason. So from a quantum mechanical point of view, dark photons and normal photons are almost the same thing. Like, how do I distinguish an electron from a proton? They have different mass and they have different charge, right? But dark photon and normal photon are both massless and they both have no charge. So why are they different? Well, they're different because they mediate forces that are felt by different types of particles. But quantum mechanically speaking, there's no rule that forbids, in some sense, one from turning into the other. And that's called kinetic mixing. Without going into details, and you might, I don't know if you'll keep this in the final interview if that's way too deep, I'm sorry. But the point is that quantum mechanically speaking, you cannot forbid, in some sense, dark photons turning into or mixing into normal photons and vice versa. And furthermore, if you try and look for from like these various quantum gravitational arguments, there's even like a rough size of this mixing that is sort of motivated, that is worth considering in particular. And that mixing is literally something on the order of 10 to the power of minus 14 to 10 to the power of minus 10. So just to put that in numbers, and by the way, because it's quantum mechanics, that has to get squared when you look at actual physics effects. Long story short, there is roughly a 1 in a trillion trillion to a 1 in a trillion 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 type of chance that a normal photon turns into a dark photon and vice versa, very colloquially speaking. So that's an insanely tiny number. So what? Well, tiny interactions can do things. It might be a way to detect this dark matter in detectors. But for the purpose of mirror stars, the reasons why it's exciting, if mirror stars exist, dark photons exist. If dark photons exist, there is no quantum mechanical reason why this tiny, 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 tiny interaction would be forbidden. And that tiny, tiny, tiny interaction essentially makes it so that normal matter has a tiny interaction with the dark atomic matter, but literally a trillionth as much as it has with other matter. And that tiny, tiny amount is still enough such that when something like a piece of hydrogen or helium or other piece of normal gas from the galaxy, if it flies through the mirror star or any kind of star, it's pretty big. It has a lot of dark atoms. It has a lot of chances for this. Imagine having a dice, that a trillion-sided dice, and if you roll a 1, then you get captured by the mirror star. Well, you roll that dice each time the normal piece of hydrogen flies past a dark atom. But there's way more than a trillion atoms in the mirror star. So the point is that a mirror star would be actually pretty good at capturing a small amount of gas as it flies through the Milky Way because of this incredibly tiny, quantum mechanically not forbidden interaction. And now you have a situation where this dark matter star that's invisible and shining in dark photons actually captured an asteroid amount, like not actually an asteroid, but an asteroid mass type of amount of interstellar gas in its core. And these tiny interactions, once the gas is trapped, are heating up the gas that's trapped in the star and making it radiate. And that is what we could see in telescopes. And it turns out that the radiation type, the emissions of this captured gas in detail are unlike anything that can be made by normal stars, normal nebulae, and so on. It's a unique spectral signature that we could use to look for mirror stars.
And by proxy, then we would know that dark photons exist, which would lend a lot of credence to the idea of a dark periodic table and a true counterpart of how matter behaves in the dark regime. Absolutely fascinating. So what's the plan on looking for this? Or do you got anybody with telescopes ready to go and try and detect this? Or can you look at data sets that already exist for something like this?
The answer is yes. So we're working. So at this point, I want to give a shout out to my awesome collaborators. So my longtime collaborator is Professor Chris Matzner at Toronto as well. He's a stellar astrophysicist. So it's kind of, as a particle theorist, I think about these theories from a sort of fundamental quantum field theory point of view, but I don't know that much about stellar physics, or I know a little bit now, but I knew almost nothing when I started. And Chris Matzner is a stellar astrophysicist who's excited by this possibility. And sort of together, we were investigating this with each of our expertise. And we've done this in collaboration with a few really awesome students. So the paper that you're referring to was together with Isabel Armstrong and Birkin Gorbutz, who are now off to PhD programs of their own. But they calculated the emission spectrum of these mirror stars. And we're currently working with another set of students to calculate this emission spectrum in a essentially once the amount of gas that's captured becomes above a certain amount, you have to do something different. Because essentially, if you capture enough gas, the captured gas becomes so dense that it's no longer transparent. So you have to calculate things differently. The point is that we're in the middle of doing these really quite precise and realistic calculations to really predict what this characteristic weird emission spectrum is of mirror stars via their captured matter. And once we have the next calculation completed, we will have the complete set of predictions, like completely general. No matter what the mirror star mass, type, temperature, you can kind of wrap all that away in a certain way and really just have a complete understanding of how the captured gas shines and looks like in telescopes. And indeed, hopefully, even maybe by the end of this year, there are public catalogs that you could use to look for these spectral signatures. There's data from the Gaia satellite that they measure billions of stars and their distances using parallax. So you could look for stars that look very faint, but they're actually very close, within, say, 100 or 1,000 light years. So something that's so faint but so close couldn't be a normal star, right? And then you look at it more carefully. So there's a variety of astrophysical observations that have already been done that could already have recorded this signal. So it becomes kind of like being an archaeologist or a paleontologist, and you're looking through university archives, artifacts or fossils buried in dusty drawers, dug up 100 years ago, or perhaps in the case of Gaia or other telescopes, a few or 10 years ago, but whatever. And you look at this for the first time with a certain eye, and you realize it for what it is. Oh, wow, you took this picture 10 years ago, but you didn't know that you actually photographed humanity's first evidence of dark matter directly in the optical. Yeah. So the first step certainly is looking at existing telescope data, because it's essentially drawers full of fossils. Some of them could be what we're looking for. Beyond that, the thing that's really interesting is that we predict that part of the characteristic emissions of this mirror star is actually certain kinds of X-rays, which is completely unique and weird. And you could look for this with certain kinds of X-ray observations. So that might motivate looking for those in various kinds of space-based missions. That's kind of the next step. So we're hoping to actually look for these, but for starters, in the huge amount of surveys and telescope data that's already been taken. And it's very possible that the evidence is already hiding there.
It's going to be amazing, because finally we have something to look for with dark matter, other than some random interaction, maybe, which we've never seen. But finally we have something to look forward to. Thank you for joining us today, David, and I hope you'll come back sometime and we can have a Fermi paradox debate or discussion. Obviously, I'm obsessed with it and have been for 40 years and still don't have an answer.
I would actually really love that. That would be great.